January 5, 1943, 05:30 hours. Kula Gulf, Solomon Islands. Lieutenant Red Cochran pressed his eye against the fire control director aboard the cruiser USS Helena, tracking 4 Aichi D3A dive bombers as they completed their attack run against the American task force. The Val bombers had just struck the New Zealand cruiser Achilles and were turning away with the characteristic precision that made Japanese naval aviators the most feared in the Pacific. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Cochran's finger moved to the firing switch. His gun crews had loaded shells containing technology that would rewrite every calculation the Imperial Japanese Navy had made about American defensive capabilities. 2 salvos thundered from Helena's aft 5-inch battery. One of the departing Japanese aircraft erupted in a ball of fire without being touched by any shell. The pilot died instantly, ripped apart by shrapnel from a projectile that exploded 70 feet away from his cockpit. He never understood what killed him. Neither did his wingmen who witnessed the impossible. Neither would the Japanese High Command for the remainder of the war. This was the first combat kill by a weapon that military historians would later rank alongside radar and the atomic bomb in strategic importance. The proximity fuse, deceptively codenamed the Variable Time or VT fuse, had just announced itself to the Pacific War. Over the next 30 months, this technology would fundamentally alter Japanese tactical doctrine, shatter their aerial offensive capability, and save tens of thousands of American lives while accelerating the empire's collapse. The transformation began not with brilliance, but with a fundamental problem that had plagued anti-aircraft gunners since aircraft first became instruments of war. December 7, 1941, Pearl Harbor, Oahu. As Japanese aircraft screamed through tropical skies at 07:55 hours, American gun crews fought back with everything available. 5-inch naval guns thundered from damaged battleships, hurling 55-pound shells skyward at attacking dive bombers and torpedo planes. Each shell required manual fuse setting, a sailor turning a wrench against a clockwork mechanism, while enemy aircraft dove through defensive fire, trying to set the timer for the precise moment the shell would reach the aircraft's altitude. Most shells exploded harmlessly in empty sky, their preset timers detonating them seconds too early or too late. Some never exploded at all, their clockwork mechanisms failing under the stress of gun launch. Others fell back to earth, their contact fuses still armed, becoming deadly projectiles aimed at the city below. In Honolulu, 9 miles from the harbor, shells weighing 55 pounds crashed through roofs, detonated in streets, tore through buildings filled with families eating breakfast. The Hirosaki family died when a 5-inch shell flew through their restaurant window during morning service. Father Jitsuo, sons Jackie and Robert, daughter Shirley, and nephew George perished instantly along with 7 young men eating at the Cherry Blossom restaurant. 3-month-old Janet Yumiko Oto became the youngest American casualty of the attack when a shell struck her home, killing her, her mother, and her aunt. By the time smoke cleared over Pearl Harbor, 68 civilians lay dead. 32 of them had been killed in Honolulu, not by Japanese bombs, but by improperly fused American anti-aircraft shells landing in the city. The tragedy illustrated with brutal clarity the inadequacy of existing technology against modern aircraft. The mathematics were unforgiving and had remained essentially unchanged since the First World War. Traditional anti-aircraft fire required 3 pieces of perfect information executed in sequence, under combat conditions while being shot at. First, optical rangefinders had to calculate exact distance to a target moving at 300 miles per hour, potentially through smoke, clouds, or tropical sun glare. Second, height-finding equipment had to estimate altitude against fast-moving targets that could climb or dive at will. Third, fire control computers, mechanical devices weighing thousands of pounds, had to calculate where the aircraft would be in the 15 to 30 seconds it took a shell to reach altitude. A sailor then manually set a clockwork time fuse, turning a wrench to adjust tiny gears that would count down the seconds. The shell was loaded into the breech, the gun fired, and the fuse mechanism counted down while the shell arced upward at 2,000 feet per second, spinning at 15,000 revolutions per minute. If all calculations were perfect, if the aircraft maintained course and speed, if the mechanical fuse functioned correctly despite experiencing 20,000 times the force of gravity during gun launch, the shell would explode near the target. The odds of destroying an aircraft were approximately 1 in 2,500 rounds fired under ideal conditions. In combat, with multiple targets maneuvering through defensive fire, with crews exhausted and equipment failing, the odds dropped catastrophically. A gun crew might fire for an entire engagement and never touch an enemy aircraft. The problem had existed since aircraft first entered warfare, but became critical as aviation technology evolved. In 1918, aircraft flew at 90 miles per hour at altitudes below 15,000 feet. By 1940, modern fighters exceeded 400 miles per hour at altitudes above 30,000 feet. The gap between gunnery technology and aerial performance had widened into a chasm that was swallowing ships whole. The British discovered this reality, facing German Ju-87 Stuka dive bombers over Dunkirk in June 1940. Ships loaded with evacuating soldiers presented perfect targets. British destroyers fired thousands of rounds skyward. Most shells exploded uselessly while German bombs found their marks with mechanical precision. British naval officers recognized the fundamental truth. Ships lacked space for additional guns. More ammunition consumed limited magazine capacity. Better fire control helped, but could not overcome the fundamental limitation of time fuses requiring perfect prediction of an aircraft's future position seconds in advance. Meanwhile, across the Atlantic, a solution was being born in a laboratory that smelled of ozone and heated vacuum tubes. August 1940. Department of Terrestrial Magnetism, Carnegie Institution, Washington, District of Columbia, Dr. Merle Anthony Tuve received an impossible assignment from the National Defense Research Committee. Born in Canton, South Dakota in 1900, educated at the University of Minnesota and Johns Hopkins, Tuve had spent his career exploring the physics of the ionosphere using radio waves. In 1925, working with Gregory Breit, he had pioneered techniques measuring the reflection of radio waves from atmospheric layers to map the structure of Earth's upper atmosphere. This work laid the theoretical foundation for radar, though neither man knew it at the time. When the National Defense Research Committee approached him in August 1940 about developing a proximity fuse for artillery shells, Tuve understood immediately that radio physics might provide the solution to a problem that had stumped weapons designers for 2 decades. The British had shared preliminary research during the Tizard mission in late summer 1940. A British delegation led by Sir Henry Tizard had arrived in Washington carrying Britain's most closely guarded secrets: cavity magnetrons for high-powered radar, jet engine designs, and theoretical work on proximity fuses. The British team had concluded that while a proximity fuse might work in rockets or bombs, which experienced relatively gentle acceleration, the forces involved in artillery made it functionally impossible. A 5-inch shell experienced acceleration of 20,000 times the force of gravity when fired. No electronic device known to exist in 1940 could survive such forces, certainly not the delicate vacuum tubes that formed the only available electronic components. A standard radio tube was 6 inches tall, contained fragile glass envelopes, and housed wire filaments thinner than human hair. At 20,000 times gravity, a 1-ounce tube would weigh 1,250 pounds for the fraction of a second it took the shell to travel down the gun barrel. Forces sufficient to turn solid steel into fragments. Tuve proposed something different: a miniature radio transmitter and receiver no larger than a pint milk bottle, installed in the nose of an artillery shell. The transmitter would broadcast continuously at high frequency. As the shell approached a target, radio waves would reflect back from the aircraft's metal skin. The frequency of the reflected signal would shift due to the Doppler effect, the same phenomenon that makes a train whistle change pitch as it passes. When the frequency shift reached a predetermined level indicating proximity to the target, an electronic circuit would close, sending current to a detonator that would explode the main charge. Simple in concept, impossible in execution given the technology of 1940. But Tuve had spent 15 years bouncing radio waves off the ionosphere 60 miles above Earth, If radio could measure atmospheric layers invisible to the eye, perhaps it could measure distance to aircraft. The project, designated Section T of the National Defense Research Committee, began on August 24, 1940 with Tuve as chairman and a handful of researchers in a laboratory at the Carnegie Institution. Their first challenge was identifying what components a working fuse required. A radio transmitter capable of operating at frequencies that would provide usable Doppler shift, a receiver sensitive enough to detect reflected signals from an aircraft several hundred feet away, an electronic amplifier to boost the received signal, a circuit to compare transmitted and received frequencies and detect Doppler shift, a power source that could provide sufficient voltage and current to operate electronic circuits, a detonator triggered by the electronic circuit, safety mechanisms to prevent premature detonation. All of this had to fit inside a space approximately 8 inches long and 2 inches in diameter. The nose of a 5-inch 38 caliber shell, the Navy's standard anti-aircraft weapon. Every component presented problems that seemed insurmountable. Vacuum tubes were the only electronic amplifying devices available in 1940. Transistors would not be invented until 1947. Integrated circuits lay decades in the future. Vacuum tubes were fragile glass envelopes containing delicate filaments and electrodes suspended in a high vacuum. Standard radio tubes were 6 inches tall and weighed several ounces. The largest tubes manufactured for rugged applications were designed for mobile military radios and could withstand 10 times the force of gravity during transport over rough terrain. The fuse required tubes that could survive 20,000 times gravity. At 20,000 times gravity, a 1-ounce tube would experience forces of 1,250 pounds for the milliseconds of gun launch, forces sufficient to crush steel bearings, forces that would turn conventional vacuum tubes into glass powder and metal shrapnel before the shell cleared the barrel. October 1940. Laboratories across America received urgent requests from the National Defense Research Committee. Western Electric Company and Radio Corporation of America were asked to develop miniaturized vacuum tubes hardened for extreme acceleration. Raytheon experimented with tube designs featuring planar electrodes that distributed forces more evenly. Engineers discovered that conventional assembly techniques produced tubes that shattered instantly under high acceleration. The solution required innovations in every aspect of tube design and manufacturing. Glass was modified with additives that increased strength while maintaining the vacuum seal necessary for tube operation. Internal components were embedded in shock-absorbing materials. Electrode structures were redesigned using spot welding techniques that created mechanical bonds capable of surviving extreme stress. By spring 1941, after thousands of design iterations and tens of thousands of test firings, acceptable tubes emerged from production lines. They measured less than an inch in height. They weighed a fraction of an ounce. They could survive 20,000 times gravity and continue functioning. They represented a complete revolution in electronics manufacturing. The power source presented equally daunting challenges. Batteries in 1940 were heavy, bulky devices filled with liquid electrolyte. They could not survive gun launch. They could not be made small enough. Harry Diamond and Wilbur Hinman at the National Bureau of Standards developed an ingenious solution that turned the problem into the answer. A glass tube filled with electrolyte solution, sealed with metal plates at each end. When the shell was at rest, the liquid remained in the center of the tube, isolated from the metal plates by the vacuum. When fired, centrifugal force from the shell's rotation, 15,000 revolutions per minute, forced the electrolyte outward against small pieces of metal embedded in the tube walls. Chemical reaction between the electrolyte and metal plates generated electrical current. The battery activated only when the shell was spinning, providing a built-in safety mechanism that prevented premature detonation. A shell sitting in a magazine was completely inert, A shell in flight became a powered radio transmitter. May 6, 1941. Dahlgren Naval Proving Ground, Virginia. 6 prototype FOSes built by the National Bureau of Standards team were loaded into air-dropped bombs and tested over water. Radio transmitters activated. Receivers detected reflections from the water's surface. Electronic circuits triggered detonators. All 6 bombs exploded at the correct altitude, approximately 70 feet above the Potomac River. The success validated the basic concept, but bombs dropped from aircraft experienced only a few hundred times the force of gravity when released. Artillery presented a challenge 2 orders of magnitude greater. By June 1941, Section T had expanded to over 100 engineers, physicists, and ordnance specialists. A former automobile dealership in Silver Spring, Maryland, became the main laboratory, with security so tight that neighbors speculated about the mysterious activities behind blackout curtains. Guards checked identification at multiple checkpoints. Workers signed documents acknowledging that disclosure of any information would result in immediate prosecution. The cover story described research into optical instruments for submarines. The reality was a crash program to develop a weapon that Allied military leaders believed could alter the course of the war. The development process revealed a cascade of engineering challenges, each one threatening to stop the entire program. The antenna had to be small enough to fit in the shell's nose while efficient enough to transmit and receive radio signals at frequencies around 180 MHz. Engineers developed a ring antenna circling the fuse body, creating an omnidirectional radiation pattern. The transmitter circuit had to generate radio frequency signals using just 3 miniaturized vacuum tubes. Circuit designers created oscillator designs that operated at 180 to 220 MHz. The receiver circuit had to detect signals 1/millionth the strength of the transmitted signal after reflection from an aircraft's metal skin. Amplifier stages using 4 vacuum tubes provided sufficient gain despite the microscopic size of each component. The Doppler detection circuit compared transmitted and received frequencies, closing an electrical contact when the difference indicated proximity to a target. This was the heart of the fuse. A circuit that could measure its own distance from a target by detecting tiny shifts in radio frequency. The entire mechanism had to function reliably after experiencing forces that would liquefy human tissue. After spinning at 15,000 revolutions per minute, after being subjected to temperatures ranging from -50 degrees Fahrenheit in high-altitude flight to +120 degrees in tropical magazines. December 7, 1941. The attack on Pearl Harbor transformed the proximity fuse project from important research to the highest national priority. The Navy had been cautiously interested in electronic fuses, witnessing the inadequacy of time fuses during the Pearl Harbor attack, watching American shells fall on Honolulu while Japanese aircraft escaped, untouched, eliminated all doubts about the need for revolutionary technology. Production contracts expanded from hundreds of thousands to hundreds of millions of dollars. The project designation changed from research to weapons procurement. Johns Hopkins Applied Physics Laboratory was founded on March 10, 1942 to centralize development and coordinate with industry. 5 companies received contracts to mass-produce fuses, following designs developed at the Applied Physics Laboratory, Crosley Corporation in Cincinnati, Ohio. Radio, Corporation of America, Eastman Kodak, General Electric, McQuay Norris. Each company committed entire factories to fuse production. Over 100 factories would ultimately participate, producing components for fuses that each contained approximately 130 miniaturized parts. The goal was 40,000 phases per day by late 1943, 70,000 per day by war's end. Production rates that seemed impossible given the precision required. Each fuse had to function reliably despite containing electronics manufactured to tolerances of 1/10,000th of an inch. The secrecy surrounding the project was absolute and enforced with military precision. Workers assembling components never knew what the final product would do. Different companies manufactured different sub-assemblies that were brought together only at final assembly plants. The designation variable time fuse was chosen specifically to mislead anyone who might learn of the project. Time fuses already existed. Variable suggested an improvement to existing technology rather than a revolutionary new concept. The code word VT fuse was used in all military communications. Even after combat use began, captured fuses that failed to detonate were assumed to be some kind of advanced time fuse by Japanese and German intelligence. Neither enemy ever determined the true nature of the technology during the war. August 12, 1942. Chesapeake Bay, Virginia. The cruiser USS Cleveland conducted the first comprehensive test of production proximity fuses against drone aircraft. The test was scheduled for 2 full days. 3 radio-controlled target drones were launched from shore facilities to simulate aerial attack patterns. Cleveland's 5-inch guns opened fire at 0800 hours. The first drone disintegrated after the second salvo. The second drone exploded after the third salvo. The third drone was destroyed on the fourth salvo. Total ammunition expenditure: 4 proximity-fused shells. Total time elapsed: less than 30 minutes. Naval authorities immediately cancelled the remainder of the 2-day test schedule. There was nothing left to test. The technology worked beyond anyone's expectations. Orders went out that same day for immediate mass production and fleet deployment at maximum possible speed. In tests over the previous 2 years, time-fused shells had scored hits requiring an average of 2,500 rounds fired per aircraft destroyed. Proximity-fused shells destroyed aircraft with just 4 rounds, a 600-fold improvement in effectiveness. The implications were staggering for naval operations in the Pacific. Production accelerated through fall 1942 despite countless technical challenges. The first combat-ready fuses reached fleet units in October 1942. The cruiser Helena received 500 rounds of proximity-fused 5-inch ammunition, carefully distributed throughout the ship's magazines to prevent catastrophic loss if the ship was damaged. Instructions emphasized that proximity fuses were to be used only over water, where unexploded shells would sink beyond enemy recovery. Gunners received training but were not told how the fuses functioned. They were told only that the new ammunition was more effective, and that discussing it with anyone would result in courts-martial. Initial fleet reaction ranged from skepticism to cautious curiosity. Gun crews had heard promises of wonder weapons before. They had fired thousands of rounds at Japanese aircraft and watched most shells explode uselessly in empty sky. They would believe the new fuses worked when they saw results. The morning of January 5, 1943 resolved all doubts in 90 seconds. Lieutenant Red Cochran's fire control solution wasn't perfect. His gun crews didn't have time for careful calculations. The 4 Japanese Val dive bombers were already departing after striking Achilles. Standard procedure was to fire a few salvos at departing aircraft, more for crew morale than any expectation of hits. Cochran ordered 2 salvos. 6 shells, the second salvo connected. 1 shell passed within 70 feet of a departing Val. The proximity fuse detected reflected radio waves from the aircraft's metal skin. Electronic circuits compared transmitted and received frequencies. Doppler shift indicated proximity. The circuit closed. The detonator fired. The main charge exploded. Fragments traveling at 3,000 feet per second tore through the Val's fuselage, severed control cables, shredded the pilot. The aircraft rolled inverted and plunged into the Kula Gulf, trailing smoke and flame. Word spread through the Pacific Fleet within hours. Helena's gun crews reported that the new ammunition actually worked. Ships that had received proximity fuses began requesting more. Commanders who hadn't received them demanded immediate allocation. The technology that had seemed impossible in August 1940 had just killed its first enemy aircraft in January 1943, 29 months from concept to combat effectiveness. American industrial mobilization had achieved what Japanese military planners believed impossible. The United States had developed sophisticated electronics that could survive artillery launch, manufactured them by the thousands, deployed them across the Pacific, and used them to kill Japanese aircraft without the enemy understanding what had changed. By March 1943, 25% of all anti-aircraft ammunition issued to the Pacific Fleet contained proximity fuses. These rounds accounted for over 50% of all Japanese aircraft destroyed by naval gunfire. The mathematics of aerial combat had shifted decisively and irreversibly against the Empire of Japan. Enemy pilots noticed something had changed in early 1943, but could not identify what. American ships seemed to shoot down aircraft at impossible ranges. Defensive fire that should have been ineffective became deadly. Aircraft maneuvering violently to avoid predicted shell bursts died anyway when shells exploded near them without direct hits. Japanese after-action reports from early 1943 documented increasing casualties to American anti-aircraft fire without understanding why. Pilots reported that American ships had improved their gunnery, perhaps through better training or new fire control systems. Some suggested American radar had improved to provide better targeting data. The truth, that individual American shells carried miniature radio transmitters that measured their own distance from targets, exceeded Japanese technological assumptions. If someone had suggested such technology existed, Japanese engineers would have dismissed it as physically impossible given the forces involved in gun launch. Proximity fuzzes proved 3 times more effective per round than conventional time fuzzes under identical conditions against fast-moving targets. In night engagements, where visual tracking was nearly impossible and time fuses relied entirely on radar-derived range estimates, the advantage increased to 7-fold. Ships previously defended by putting up walls of steel, relying on volume of fire to achieve occasional hits, could now achieve aerial kills with a fraction of the ammunition expenditure. This had profound implications for naval operations. Magazines could hold more rounds because fewer were needed per engagement. Ships could stay on station longer without returning to port for ammunition resupply. Gun barrels lasted longer because fewer rounds were fired per kill, reducing wear. The effectiveness of proximity fuses triggered Japanese tactical changes that Allied intelligence observed but could not fully explain without revealing the secret. Japanese aircraft began attacking from higher altitudes in spring 1943, sacrificing bombing accuracy to remain outside, what they perceived as improved American anti-aircraft range. Torpedo bombers approached at wave-top altitude where they hoped to achieve surprise, though this also worked against them because radio reflections from the ocean surface sometimes caused premature detonations that created waterspouts that damaged low-flying aircraft. Dive bombers released at steeper angles to minimize exposure time to defensive fire. These adaptations reduced Japanese strike effectiveness while failing to restore the tactical advantage they had enjoyed earlier in the war. American ships continued to shoot down Japanese aircraft at rates that made conventional attacks increasingly unsustainable. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Admiral William Halsey, commanding South Pacific Forces, credited proximity fuses with fundamentally changing the naval balance of power in theater reports that remained classified for decades. Japanese torpedo bombers, which had been particularly effective in night attacks when visual tracking was difficult and time fuses were nearly useless, found themselves facing ships that could engage aircraft effectively in total darkness using radar detection and proximity fuses. During 1943, despite using proximity fuses in only 25% of ammunition expended, over half of Japanese aircraft destroyed by anti-aircraft fire were killed by proximity-fused shells. The statistical evidence was overwhelming. The fuses worked. They worked so well that American naval commanders began requesting more allocation than production could provide. Production facilities operated 24 hours daily, 7 days per week. Crosley Corporation's Cincinnati plant employed 8,000 workers, producing up to 16,500 proximity fuzzes daily at peak production. Their quality control detected defects measuring 1/5,000th of an inch. The plant consumed more electricity daily than entire German cities, running precision machinery that manufactured components to tolerances previously considered impossible for mass production. Air conditioning maintained temperature within 2 degrees Fahrenheit to prevent thermal expansion affecting tolerances. Humidity was controlled to prevent moisture from affecting electronic components. Clean rooms with filtered air prevented dust particles from contaminating miniaturized vacuum tubes. Workers wore special clothing and used microscopes to verify component placement within tolerances of 1/20,000th of an inch. Quality control rejected 28% of completed units that failed to meet specifications. This rejection rate, which would have been catastrophic in German or Japanese production, was acceptable to American planners because production volume was so massive. American factories could afford to destroy more precision electronic components daily than Japan produced monthly across all industries. Sylvania dominated component manufacturing, producing 95% of the miniaturized vacuum tubes, over 100 million total, employing 10,000 workers across 15 plants dedicated solely to the VT program. Over 100 American companies participated across the supply chain, with more than 2,000 suppliers, ranging from copper wire manufacturers to precision machine shops, making components measured in thousandths of an inch. The workforce was predominantly female. At Sylvania's Ipswich, Massachusetts plant, 9,000 of 10,000 workers were women, many recruited from local communities with no prior industrial experience. They worked in clean rooms with filtered air, using microscopes to verify component placement within tolerances of 1/20,000th of an inch. Each worker typically performed one specific task, repeated thousands of times per shift, assembling components. They never fully understood into weapons that would kill enemy pilots an ocean away. This was American industrial democracy, functioning at peak efficiency. Free citizens manufacturing sophisticated weapons to defend freedom against totalitarian aggression. The irony would not be lost on Japanese commanders when they learned after the war that American women assembling proximity fuses in Massachusetts factories had killed more Japanese pilots than entire Japanese aircraft production facilities could replace. The Pacific War entered a new phase in late 1943. Japanese naval aviation, which had dominated the early war through superior training and aggressive tactics, found itself unable to sustain operations against American ships equipped with proximity-fused ammunition. The mathematical realities were unforgiving. Japanese aircraft production could not replace losses at the rate American proximity fuses inflicted them. Japanese pilot training programs could not produce replacements fast enough to maintain operational strength. Each experienced pilot killed by proximity-fused anti-aircraft fire represented thousands of hours of training and years of experience that could never be recovered. By early 1944, Japan was committing partially trained replacement pilots who fell victim to American defenses at unsustainable rates. The Battle of the Philippine Sea in June 1944 demonstrated how completely proximity fuses had tilted the balance. American carriers operating in the Philippine Sea came under sustained attack by Japanese naval aircraft flying from bases in the Marianas. American ships fired proximity-fused ammunition without restriction. The result became known as the Great Marianas Turkey Shoot. Over 400 Japanese aircraft were destroyed in 2 days of combat. American ships firing proximity-fused shells accounted for a significant percentage of kills. The destruction was so complete that Japanese naval aviation never recovered. The handful of experienced pilots who survived returned to their carriers with reports that seemed impossible. American ships destroying aircraft at ranges previously considered safe, defensive fire that followed maneuvering aircraft through evasive action, shells that exploded without direct hits, showering aircraft with fragments that shredded control surfaces and killed pilots. Japanese intelligence officers questioned survivors about American anti-aircraft effectiveness. The reports were consistent but inexplicable. Something had changed. American gunnery had improved dramatically. But how? Japanese engineers examined fragments recovered from aircraft that limped back to base. The fragments showed nothing unusual. Standard American high-explosive shells, nothing revolutionary in metallurgy or explosive composition. Some Japanese engineers speculated about radio-controlled shells, but dismissed the concept as requiring too much sophistication for battlefield use. The idea that individual shells carried miniature transmitters that measured their own distance from targets exceeded Japanese assumptions about what American electronics could achieve under combat conditions. This failure of imagination, This inability to conceive that the United States had miniaturized sophisticated electronics to fit inside artillery shells that experienced 20,000 times the force of gravity allowed the proximity fuse to remain operationally secret throughout the remainder of the war. October 1944. The Philippines. Japanese forces facing inevitable defeat implemented a strategy that would test American defenses to absolute breaking point. Special attack units, officially termed Shinpu Tokubetsu Kogekitai but known universally as kamikaze, began deliberate suicide attacks against American ships. The first organized kamikaze attacks struck during the Battle of Leyte Gulf. The tactic was born from desperation and Japanese recognition that conventional attacks had become militarily impossible. Experienced pilots had been systematically destroyed over 2 years of attrition warfare. Replacement pilots received minimal training, insufficient for precision bombing and torpedo attacks that required extensive skill. Kamikaze attacks required only enough proficiency to keep an aircraft pointed at a target while dive bombing through defensive fire. No bombs to aim, no torpedoes to drop at precise distance and angle, no escape maneuver to execute. Just one skill: fly straight into the target until impact. Proximity fuses proved essential against kamikaze attacks, though their effectiveness was complicated by the nature of the threat itself. Conventional attacks saw aircraft approach, release weapons, and attempt escape. Proximity fuses destroyed attackers at distances where damaged aircraft would miss their targets. Damaged pilots would break off attacks to return to base. Kamikaze attacks removed the escape calculation entirely. Pilots flying damaged aircraft continued toward targets regardless of injuries. Aircraft with control surfaces shot away, engines failing, fuselages riddled with fragments, kept coming. Sometimes surviving long enough to crash into ships, even after sustaining damage that would have caused conventional attackers to abort. The solution required concentration of fire that destroyed aircraft completely rather than merely damaging them. Ships increased rates of fire, created denser patterns of proximity-fused shells, and engaged targets at longer ranges. The mathematical challenge was unforgiving. A kamikaze had to be literally shot from the sky, reduced to falling debris, before reaching its target. The destroyer USS Hadley and destroyer escort USS Evans, operating as radar pickets, faced 156 attacking aircraft on May 11, 1945, during 90 minutes of sustained assault. Hadley destroyed 12 aircraft before being struck by 4 kamikazes that remained airborne long enough to crash into the ship, despite being hit multiple times by anti-aircraft fire. Evans destroyed 23 aircraft before damage forced withdrawal. Post-action analysis showed that proximity fuses had been indispensable, destroying aircraft at ranges where time fuses would have been completely ineffective. Without proximity fuses, both ships would certainly have been sunk in the first 30 minutes of engagement. Statistical analysis from the Pacific War documented effectiveness precisely. Between October 1944 and August 1945, American naval forces destroyed 278 Japanese aircraft using proximity-fused ammunition. Analysis showed that only 46 would have been destroyed using conventional time fuses under identical circumstances. The 6-to-1 effectiveness ratio translated directly to lives saved and ships kept operational. The calculation was simple and brutal. Ships using conventional time-fused ammunition required an average of 1,162 rounds per aircraft kill. Ships using proximity-fused ammunition required 310 rounds per kill. At Okinawa, where American ships faced the most intensive kamikaze operations of the war, proximity fuses accounted for significant percentages of Japanese aircraft destroyed, though the majority of kills still came from combat air patrols and shorter-range automatic weapons. The Navy lost 21 ships sunk and 66 damaged during the Okinawa campaign. 2/3 of damaged ships were still being repaired when the war ended. The human cost was staggering. Thousands of American sailors died in kamikaze attacks, but without proximity fuses, the casualties would have been catastrophically worse. Every Japanese aircraft shot down by VT-fused shells was one that didn't crash into American ships. Every ship saved meant hundreds of sailors who survived the war. Japanese intelligence never fully understood why. American anti-aircraft effectiveness had increased so dramatically after early 1943. Post-war interrogations of Japanese military officials revealed that most believed Americans had developed superior fire control radar or had integrated aircraft detection with gun directors in ways Japan could not match. Some Japanese engineers speculated about radio-controlled shells, but dismissed the concept as technically impossible, given the forces involved in gun launch. The idea that individual shells could carry miniaturized radar systems, measuring their own distance from targets, seemed beyond credible technology for battlefield deployment. This failure of imagination, this inability to conceive that the United States had miniaturized sophisticated electronics to fit inside artillery shells, experiencing 20,000 times the force of gravity, allowed the proximity fuse to remain operationally secret throughout the war. The broader impact of proximity fuse technology extended far beyond World War II into modern military development. The techniques developed for miniaturizing electronics and hardening components to survive high acceleration became foundational for subsequent advances. Missile guidance systems, space exploration, and modern artillery all benefited directly from innovations pioneered by the proximity fuse program. The concept of distributed intelligence, where individual munitions carry sophisticated sensors and processors, traces directly to VT fuses. Modern smart munitions that can sense targets, discriminate between targets, and optimize detonation represent evolution of principles established between 1940 and 1945. Dr. Merle Tuve, returning to the Carnegie Institution after the war, rarely spoke publicly about his role developing proximity fuses. When details were finally released for publication in September 1945, Tuve deflected personal credit, emphasizing the contributions of hundreds of engineers and thousands of production workers who transformed theoretical concepts into millions of reliable fuses. His modesty understated his essential leadership in a program that War Department officials ranked second only to the atomic bomb in strategic importance. Without his insight that radio proximity detection could be miniaturized sufficiently for artillery shells, without his persistence through early failures when success seemed physically impossible, the proximity fuse would have remained theoretical rather than combat reality. The production achievement equaled the technical accomplishment in significance. Manufacturing 22 million proximity fuses, each containing 130 precision components, required industrial organization on unprecedented scale. Over 100 factories had to coordinate delivery of components, matching specifications measured in thousandths of an inch. Supply chains had to deliver vacuum tubes, batteries, and electronic components from hundreds of specialized suppliers, all synchronized to keep assembly lines operating at maximum capacity 24 hours daily. At 70,000 fuses per day peak production, the program required approximately 9 billion total electronic components manufactured over the course of the war. Each component had to function reliably after experiencing forces that would destroy conventional electronics. Each had to operate in temperatures ranging from Arctic cold to tropical heat. Each had to survive months of storage in conditions ranging from humid Pacific islands to frozen European depots. The proximity fuse stands alongside radar and penicillin as technologies that materially affected World War II's outcome. Unlike radar, whose development occurred in multiple countries simultaneously, the proximity fuse resulted from deliberate application of American scientific and industrial capability to a specific problem. Dr. Tuve and his team at Section T identified what needed accomplishment, determined how to execute it, and led a program that achieved operational capability in under 3 years. This focused approach to weapons development became the model for Cold War military research. The Manhattan Project, developing atomic weapons, followed similar organizational patterns. Post-war missile programs adopted the same structure of university laboratories, industrial contractors, and military oversight, coordinating to achieve goals that seemed impossible at program inception. The legacy of those 20,000 G-rated fuses extends beyond their combat effectiveness into how nations organize scientific talent for military objectives, how industries manufacture precision electronics at scale, and how seemingly impossible technical challenges yield to sustained effort, backed by adequate resources and talented people working toward common purpose. The miniaturized vacuum tubes that seemed impossible in 1940 became routine by 1945. The precision manufacturing that required specialized technicians became increasingly automated as production techniques advanced and lessons were applied to post-war industries. But in 1943, 1944, and 1945, as Japanese aircraft fell from Pacific skies, as German infantry died under precisely timed airbursts in Europe, as V-1 missiles disintegrated over the English Channel, the proximity fuse represented the cutting edge of what human ingenuity, backed by industrial democracy, could achieve. However, not all American secrets remained secure. While proximity fuses devastated Axis forces, Soviet intelligence was actively working to acquire the technology. Julius Rosenberg, an electrical engineer working as an inspector for the Army Signal Corps at Emerson Radio, provided his Soviet handler with thousands of classified documents. Among the most significant intelligence Rosenberg passed to the Soviets was a complete working model of a proximity fuse. According to declassified Soviet intelligence documents and testimony from his handler Alexander Feklisov, Rosenberg delivered detailed technical specifications, component designs, and manufacturing processes. The irony was profound. While American proximity fuses were killing Japanese pilots and German soldiers by the thousands, Soviet engineers were reverse engineering captured samples and studying intelligence provided by American traitors. The technology that helped defeat fascism would eventually be turned against American forces. Soviet development of their own proximity fuses took years despite having working examples and detailed technical documentation. Even with complete specifications, Soviet industry lacked the precision manufacturing capability, quality control systems, and component miniaturization expertise to mass-produce reliable fuses. Soviet engineers spent 7 years after the war reverse engineering captured American proximity fuses before successfully producing indigenous versions in 1952. Even then, quality remained inferior to American wartime production. This technological transfer pattern revealed the complexity of proximity fuse manufacturing. Having examples and documentation wasn't sufficient. Successful production required industrial infrastructure, specialized machine tools, trained workforce, and manufacturing expertise that took years to develop, even with detailed blueprints to follow. The story of proximity fuses ultimately reveals truths about industrial warfare that transcend any single technology. First, evolutionary improvements to existing systems can be more decisive than revolutionary new weapons. Proximity fuses were still artillery shells, fundamentally unchanged externally, but they transformed artillery effectiveness completely. Second, mass production capability matters as much as technological sophistication. Germany developed jet aircraft, ballistic missiles, and advanced submarines, but couldn't manufacture them in decisive quantities. America produced millions of proximity fuses, each one a sophisticated electronic device, and treated them as expendable ammunition. Third, industrial integration determines military capability more than isolated technical achievements. The proximity fuse required coordinated effort from scientists, engineers, manufacturers, and military users. American organizational culture facilitated this integration. Axis institutional rivalries and resource constraints prevented equivalent achievement. Finally, technological surprise has immense operational value. Restricting proximity fuse use over land until December 1944 preserved tactical surprise against German forces, though it meant months of additional Allied casualties that might have been prevented by earlier deployment. The proximity fuse raises complex questions about technological warfare that remain relevant. It made killing more efficient, more certain, more mathematically precise. Japanese pilots flying to their deaths in kamikaze attacks had no defense against shells detonating nearby at precisely calculated distances. German soldiers in foxholes were equally helpless against airbursts. This wasn't combat in any traditional sense where skill and courage determined outcomes. It was industrial capability manifest as physics, mathematical certainty applied to human flesh. Yet proximity fuzzes also shortened the war. Every Japanese aircraft shot down was one less attacking American ships. Every German division destroyed by proximity-fused artillery was one less defending concentration camps. The technology that efficiently killed Axis soldiers also hastened liberation of Nazi victims and ended Japanese aggression. Admiral James Forrestal, Secretary of the Navy, stated after the war that the proximity fuse helped blaze the trail to Japan, noting that without the protection this device provided to surface ships, the westward advance could not have been so swift, and the cost in men and ships would have been immeasurably greater. Admiral Arleigh Burke, who commanded destroyers in the Pacific, recalled that all 5-inch ammunition in 1945 was fitted with proximity fuses, and those fuses knocked down enemy planes by dozens, preventing ship losses and casualties that would have been enormously larger without this technology. British Prime Minister Winston Churchill noted that proximity fuses made in the United States proved potent against the V-1 rockets that assailed Britain in 1944, saving London from devastation that would have killed tens of thousands of civilians. The proximity fuse transformed more than World War II. It initiated the age of smart weapons that defines modern warfare. Modern precision-guided munitions trace their lineage directly to the miniaturized electronics first deployed in proximity fuses. The concept of putting intelligence into ammunition, revolutionary in 1944, is now standard military practice across all advanced militaries. The manufacturing techniques developed for proximity fuses influenced post-war electronics production profoundly. The quality control standards, clean room procedures, and precision assembly methods became foundations for the semiconductor industry that would transform global civilization. The women who assembled proximity fuses in 1944 pioneered techniques still used in electronics manufacturing today. Their contribution to victory extended beyond the immediate war into the technological revolution that followed. The organizational lessons proved equally enduring for American military-industrial development. The integration of academic research, industrial production, and military application became the model for Cold War weapons development and continues influencing defense programs today. The proximity fuse program demonstrated that democratic societies could mobilize technology as effectively as totalitarian states, perhaps more effectively because free inquiry and voluntary cooperation prove more productive than coercion over sustained campaigns. Lieutenant Red Cochran, watching that first Japanese VAL disintegrate on January 5, 1943, understood that something fundamental had changed in aerial combat, though he couldn't know the full implications. His gun crew had destroyed an aircraft without perfect aim, without precise fuse setting, without any of the calculations that had limited anti-aircraft effectiveness for decades. The shell had done the work independently, sensing the target, timing its own detonation, achieving what human gunners could only approximate through volume of fire and statistical probability. In that moment, off Guadalcanal, the age when individual munitions carried sufficient intelligence for autonomous operation had arrived. The story of the proximity fuse proves that sometimes the greatest victories are won not through revolutionary platforms, but through incremental improvements manufactured at scale, not through propaganda, but through engineering excellence, not through hatred, but through the application of scientific method to brutal realities of industrial warfare. The German soldiers and Japanese airmen who faced proximity fuses never understood what killed them. They reported only that American defenses had become impossibly accurate, that ships seemed able to shoot down aircraft regardless of maneuvering, that artillery created explosions that seemed to seek targets with mechanical precision. The proximity fuse did not win the war alone. No single technology determined the outcome of global conflict involving millions of combatants across multiple theaters, but it contributed to victory in ways that saved thousands of American lives, accelerated Axis defeat by making their offensive operations militarily unsustainable, and demonstrated American industrial supremacy. Those 20,000 G-rated fuses, each one representing the technological limits of 1940s science applied to the problem of aerial warfare, turned American 5-inch guns into weapons systems that enemy forces never expected and could never effectively counter once deployed. They remain testament to what free societies can achieve when scientific curiosity, industrial capacity, and strategic necessity align in pursuit of goals worthy of extraordinary effort. The transformation of a theoretical concept into millions of reliable devices deployed globally within 3 years stands as one of the remarkable achievements of 20th century technology. The proximity fuse killed more than Axis soldiers and pilots. It killed the assumption that traditional warfare could continue unchanged into the modern era. It killed the belief that courage and skill alone could overcome technological superiority. It killed the concept that small electronics couldn't survive battlefield conditions. From the moment Helena's guns destroyed that first Val dive bomber off Guadalcanal, warfare had changed permanently. The shells that exploded 70 feet from Japanese aircraft delivered democracy's argument against totalitarianism in fragments of supersonic steel, proving that societies valuing individual freedom and scientific inquiry could outproduce, out-innovate, and ultimately outfight authoritarian powers. The proximity fuse was ultimately democracy's perfect weapon for industrial warfare, sophisticated yet mass-produced at unprecedented scale, complex yet reliable across extreme conditions, expensive yet treated as expendable ammunition. It killed efficiently, not through hatred but through engineering excellence. It ended battles not through barbarism but through applied mathematics. It won engagements not through cruelty but through industrial capability that totalitarian systems could not match. Every Japanese pilot who died from proximity fuse airbursts, every kamikaze that fell short of its target, died, encountering the physical manifestation of American industrial democracy, a system that could conceive revolutionary technology, develop practical applications, manufacture millions of sophisticated devices, and deploy them globally while simultaneously fighting a two-ocean war against powerful enemies. The 70 feet between shell detonation and aircraft represented more than distance. It represented the gap between American capability and Axis assumptions about democratic weakness. In that brief space, measured by radio waves and timed by miniaturized electronics, lay the difference between free inquiry and totalitarian limitation. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.